Large power generation systems typically utilize a Y, also known as star, configuration. This configuration offers a zero-sequence path for fault currents, a critical feature for protecting equipment and maintaining system stability. The Y configuration also simplifies voltage regulation through the implementation of grounded transformers. The power grid is not universally configured identically. Different regions have varying voltage requirements and grid configurations. However, a prevalent configuration is the three-phase delta system. Delta systems excel at providing a high power transfer capacity and demonstrate increased efficiency in managing unbalanced loads. A drawback of delta systems is the absence of a zero-sequence path for fault currents. In some regions, a wye-delta system is adopted, combining the strengths of both configurations. Generators connect to the grid via the Y configuration, while the delta configuration facilitates power distribution to consumers. This hybrid system provides both fault protection and efficient power transfer. Voltage levels in power generation and distribution systems exhibit substantial variability based on distance and system size. Common voltage levels are observed in firstly, distribution systems which utilize 120/240 volt single-phase and 208 Y/120 volts three-phase. Secondly, transmission systems which operate at 138 kV, 230 kV, and 500 kV three-phase. And thirdly, generation systems operating up to 25 kV three-phase. When discussing power systems, it's essential to understand the role of transformers. Transformers are used to step up or step down voltage levels. Step-up transformers increase voltage from generation levels to transmission levels, reducing current and minimizing losses during long-distance transmission. Step-down transformers decrease voltage from transmission levels to distribution levels for safe use by consumers. The choice between Y and delta configurations also affects transformer connections. Y-Y, delta-delta, wye-delta, and delta-Y transformer connections are all commonly used in power systems. Each connection type has specific characteristics regarding voltage and current relationships, as well as their ability to handle unbalanced loads and provide a path for ground currents. Grounding is a critical aspect of power system design. Grounding provides a low-impedance path for fault currents to flow back to the source, allowing protective devices, such as circuit breakers and fuses, to quickly detect and interrupt the fault. Grounding also helps to limit voltage rise during fault conditions, reducing the risk of electric shock. Different grounding methods are used in power systems, including solid grounding, resistance grounding, and reactance grounding. The choice of grounding method depends on factors such as system voltage, fault current levels, and the desired level of protection. Protection schemes are implemented in power systems to detect and isolate faults. These schemes typically involve the use of protective relays, which monitor voltage and current levels and trip circuit breakers to clear faults. Protection schemes are designed to be selective, meaning that they should only trip the circuit breakers that are necessary to isolate the fault, minimizing the impact on the rest of the system. Common types of protective relays include overcurrent relays, overvoltage relays, undervoltage relays, and differential relays. Power system stability is the ability of the system to maintain synchronism following a disturbance, such as a fault or a sudden change in load. Stability is affected by factors such as generator inertia, transmission line impedance, and the control systems used to regulate voltage and frequency. Power system operators use a variety of tools and techniques to monitor and maintain system stability, including power flow studies, transient stability studies, and voltage stability studies. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency. Harmonics are typically caused by nonlinear loads, such as electronic devices and variable speed drives. Harmonics can cause a variety of problems in power systems, including increased losses, equipment overheating, and interference with communication systems. To mitigate harmonics, harmonic filters are often installed. These filters consist of capacitors and inductors that are tuned to specific harmonic frequencies, providing a low impedance path for harmonic currents to flow. Power quality refers to the characteristics of the voltage and current in a power system. Good power quality is essential for the reliable operation of sensitive electronic equipment. Power quality problems include voltage sags, voltage swells, transients, and harmonic distortion. Power quality monitoring equipment is used to detect and diagnose power quality problems. Power factor correction is the process of improving the power factor of a load. Power factor is the ratio of real power to apparent power. A low power factor indicates that the load is drawing a large amount of reactive power, which does not do useful work. Power factor correction is typically achieved by adding capacitors to the load. These capacitors provide reactive power, reducing the amount of reactive power that must be supplied by the utility. Power factor correction can improve the efficiency of the power system and reduce energy costs. Distributed generation refers to the generation of electricity at or near the point of consumption. Distributed generation can include renewable energy sources such as solar panels and wind turbines, as well as combined heat and power systems. Distributed generation can reduce reliance on the central power grid, improve energy security, and reduce greenhouse gas emissions. Microgrids are localized energy grids that can operate independently from the main power grid. Microgrids typically include distributed generation sources, energy storage systems, and control systems. Microgrids can provide reliable power to critical loads, such as hospitals and emergency services, during grid outages. Smart grids are power grids that use advanced communication and control technologies to improve efficiency, reliability, and security. Smart grids can enable features such as real-time pricing, demand response, and advanced metering infrastructure. Smart grids can also facilitate the integration of renewable energy sources and distributed generation. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. The NEC provides detailed requirements for conductor sizing, overcurrent protection, grounding, and other aspects of electrical installations. Compliance with the NEC is essential for ensuring the safety of people and property. When dealing with electrical installations, understanding conductor ampacity is crucial. Ampacity refers to the current carrying capacity of a conductor expressed in amps. The NEC provides tables such as Table 310.15b16 that list the ampacities of various conductors based on their size, insulation type, and ambient temperature. It's important to select conductors with adequate ampacity to prevent overheating and potential fire hazards. Overcurrent protection is another vital aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. The NEC requires that overcurrent protective devices be sized to protect conductors from overload and short-circuit conditions. Grounding is essential for providing a low-impedance path for fault currents to flow back to the source, allowing overcurrent protective devices to quickly clear the fault. The NEC specifies the requirements for grounding electrode systems, grounding conductors, and equipment grounding. Arc flash is a dangerous phenomenon that can occur when a short circuit creates a high-energy arc. Arc flash can cause severe burns, injuries, and even death. The NEC requires that electrical equipment be labeled with arc flash hazard warnings and that qualified personnel use appropriate personal protective equipment when working on energized equipment. Electrical safety training is essential for all personnel who work on or near electrical equipment. Training should cover topics such as electrical hazards, safe work practices, personal protective equipment, and emergency procedures. Qualified personnel should be trained and certified to perform specific electrical tasks. Regular inspections and maintenance are necessary to ensure the continued safe operation of electrical systems. Inspections should be performed by qualified personnel and should include a visual examination of electrical equipment, testing of overcurrent protective devices, and verification of grounding connections. Maintenance should include cleaning, tightening connections, and replacing worn or damaged components. Understanding voltage drop is essential for ensuring that electrical equipment receives adequate voltage. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. The NEC recommends limiting voltage drop to no more than 5% for feeders and branch circuits. Calculations should be performed to determine the voltage drop in a circuit, and conductor should be sized accordingly. Conduit is used to protect electrical conductors from physical damage and environmental factors. The NEC specifies the types of conduit that are permitted for various applications. Conduit must be properly supported and installed to prevent damage and ensure the integrity of the electrical system. Wiring methods refer to the techniques used to install electrical conductors. The NEC specifies the permitted wiring methods for various applications. Common wiring methods include conduit, cable, and surface raceway. Wiring methods must be installed in accordance with the NEC requirements to ensure safety and reliability. Electrical boxes are used to enclose electrical connections and provide a safe and accessible point for making splices and terminations. The NEC specifies the requirements for electrical boxes, including their size, material, and location. Electrical boxes must be properly grounded and secured to prevent damage and ensure the integrity of the electrical system. Control systems are used to automate and control electrical equipment. Control systems can range from simple on/off switches to complex programmable logic controllers. Control systems can improve efficiency, reduce energy consumption, and enhance safety. Power distribution units, or PDUs, are used to distribute power to multiple devices in data centers and other critical facilities. PDU typically include circuit breakers, power monitoring, and remote control capabilities. PDU can help to improve power reliability and efficiency. Uninterruptible power supplies, or UPSs, are used to provide backup power to critical equipment during power outages. UPS typically include batteries, inverters, and control systems. UPS can ensure that critical equipment continues to operate during power outages, preventing data loss and downtime. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power line disturbances, and other events. SPD can help to prevent damage to sensitive electronic equipment. Lighting is an important aspect of electrical design. The NEC specifies the requirements for lighting installations, including the number and location of lighting fixtures, the type of lighting fixtures, and the control of lighting. Lighting can improve safety, productivity, and aesthetics. Electric motors are used to power a wide variety of equipment, including pumps, fans, and compressors. The NEC specifies the requirements for electric motor installations, including motor protection, motor control, and motor wiring. Electric motors must be properly selected and installed to ensure reliable and efficient operation. Heating, ventilation, and air conditioning systems, or HVAC systems, are used to control the temperature and humidity in buildings. HVAC systems typically include electric motors, heating elements, and control systems. HVAC systems must be properly designed and installed to ensure efficient and comfortable operation. Renewable energy systems, such as solar panels and wind turbines, are becoming increasingly popular. The NEC specifies the requirements for renewable energy system installations, including the interconnection of renewable energy systems to the power grid. Renewable energy systems can reduce reliance on fossil fuels and lower energy costs. Energy storage systems, such as batteries and flywheels, are used to store energy for later use. Energy storage systems can improve power reliability, reduce energy costs, and facilitate the integration of renewable energy sources. The demand for electricity is constantly growing, and it is important to use electricity efficiently. Energy efficiency measures can reduce energy consumption, lower energy costs, and reduce greenhouse gas emissions. Electrical engineers play a critical role in designing, installing, and maintaining electrical systems. Electrical engineers must have a strong understanding of electrical theory, electrical codes, and electrical safety practices. Electrical technicians assist electrical engineers in the installation, maintenance, and repair of electrical systems. Electrical technicians must have a strong understanding of electrical safety practices and be able to work with a variety of electrical tools and equipment. The electrical industry is constantly evolving, and it is important to stay up to date on the latest technologies and trends. Continuing education and professional development are essential for electrical engineers and technicians. The safety of people and property depends on the proper design, installation, and maintenance of electrical systems. It is important to follow electrical codes and safety practices to prevent electrical hazards. Working with electricity can be dangerous, and it is important to take precautions to protect yourself from electrical shock and other hazards. Always de-energize equipment before working on it, and use appropriate personal protective equipment. If you are not qualified to work on electrical equipment, do not attempt to do so. Call a qualified electrician.